Welcome and thank you for joining. In this lesson, we'll explore the concept of the derivative of a function. Let's start with the meaning of the word derivative. To find the derivative of a function means to find how fast the y values of a function are changing at any point. So in other words, we're going to say that to find the derivative of a function means to find the speed of y values in a function. So when we think of the word derivative, I want us to think of the word speed. And remember that this is not the first time we've mentioned the speed of change of y values in a function. We learn how to measure this by using what we call the instantaneous rate of change of a function at a point, which we did with the help of the slope of a tangent line drawn at a point on the graph of a function. So remember, derivative means speed of change of y values, or instantaneous rate of change of a function, or the slope of the tangent drawn at a point on the graph of a function. Next, what notation do we use for the derivative of a function? Well, because many mathematicians analyze derivatives in different places, slightly different times, each of them came up with their own definition or notation. And we're going to start off with Lagrange's notation, a French mathematician who called the derivative f prime x. So he used an apostrophe and he called it prime. We'll talk about why this is called prime in the upcoming lessons. And by this we mean the rate of change of the y values, or the rate of change of f of x. Now here's Lagrange. I brought this just so we can put a face to the name. And next we're going to move on to Leibniz notation. Here is Leibniz, a German mathematician who described the derivative of a function by the notation dy dx, which means this is the derivative of y values differentiated in terms of x. Now, alternative ways to describe the derivative of a function in Leibniz notation are ddx of y. As you can see, the ddx replaces the prime or the apostrophe from Lagrange's notation, or ddx of the function f of x, where ddx actually is not a fraction, is just a symbol to notate the derivative of a function. Now lastly, we have Newton's notation. We got to bring Newton down here. And in Newton's notation, we're all familiar with his face. We've probably seen it in the physics textbook a lot. So Newton described the derivative of a function with this letter y with a small stress in here. It looks like an apostrophe on top of it. Now, how do we determine the derivative of a function? So we are going to analyze derivatives of various groups of functions, and we'll come up with formulas for each group of functions. But to determine, or at the roots of the derivative, or finding the derivative of a function, will always stay what we call the first principles formula. So the first principles formula states that the derivative of a function, f prime x, I use Lagrange's notation here, is the same as the slope of the tangent drawn at x, and it is measured by the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this is the slope of the tangent formula by using limits, and that represents the derivative of a function. Now, the reason why we call this the first principles formula is because this formula can help us find the derivative of any function with no discrimination about what group the function belongs to. And we are going to practice this very formula to differentiate, or to prove, or to discover, I should say, the derivative of the function f of x equals x to the power of n, which is part of differentiating polynomial functions. Remember that polynomial functions are in the form f of x equals x to some power, and we can have more than one term. So we can have a lot of terms added or subtracted, and they all will look something like this. So let's get started with differentiating f of x equals x to the power of n. And I love doing proofs because proofs help us understand how a formula has come to this world. And in the meantime, understanding this builds trust and faith in using the formula, and it deepens our understanding and appreciation, I must say, about the formula itself. So we're going to say that f prime x, according to the first principles formula, is measured by the slope of the tangent, which we are drawing at any point x, so we are not choosing a specific point, and it is measured as the limit as h approaches 0 of f of x plus h minus f of x divided by h. I'm pretty sure you're going to love this. So let's apply this formula to this function, or in other words, let's bring this function to this formula. So that would equal the limit as h approaches 0 of horizontal line, we have x plus h to the power of n. This would be f of x plus h. So since f of x is x to the power of n, the x value in the function is replaced by x plus h. So let's make a point by highlighting this. So f of x plus h is x plus h to the power of n. Now, minus f of x. So f of x is x to the power of n. So minus x to the power of n divided by h. Now, as you can see, this is an indeterminate form limit because as h approaches 0, the denominator becomes 0, which makes this indeterminate. So we'll have to search for ways to simplify h. So the way we've done this priorly with other polynomial functions was by expanding this expression. So we have a binomial brought to the power of n. And to expand this, we're going to ask for help, Pascal's triangle. So let me go over Pascal's triangle one more time just to refresh our memory. Pascal's triangle, which is built very easily by simply adding the numbers above, in the row above. So we have 1, 1, 1, 1, 2, 1. I'm going to go one more row, 1, 3, 3, 1. So remember, 1 plus 2, 3, 2 plus 1, 3, 1 plus nothing, 1. And this one here also comes from 1 plus nothing. I'll go one more row, so 1, 4, 6, 4, 1. And remember that when we expand a binomial a plus b to the power of 0, the answer was 1. So that's why we call this the row 0, because it helps us expand a plus b to the power of 0. For a plus b to the power of 1, we use the row 1. So this would be for a plus b power 2, a plus b power 3, a plus b power 4, and I'm going to write them down on the side here. So a plus b power 0, a plus b power of 1, a plus b power of 2, a plus b power of 3. I'm going to stop somewhere. Don't worry. Okay, so I want to bring to your attention now how this is a 1, all right, and this is also a 1 here. This is a 2, this is a 2. We're just emphasizing the patterns. 3, there goes a 3. 4, there goes a 4. So based on this pattern, we're going to build the nth row. So in the nth row then, we must have 1, that's what we start with. And if we are expanding a plus b to the power of n, it means that the next number in the triangle has to be n. And another thing is, I want to bring your attention right here on the last number. You see 4, 4, 3, 3, which means that the last number in the nth row will be 1, and the second last number has to be n. So it follows the same pattern. And we're going to have a bunch of numbers in here, but we don't want to talk about all of them because that takes a lot of time. And this would be sufficient enough for us to expand x plus h to the power of n. So let's expand this together. So here we go. We're going to write here the limit as h approaches 0. Long, long line. So we are expanding x plus h to the power of n, which means that x to the power of n will be the first term. H will be to the power of 0 here. The coefficient will be, take a look at this, the coefficient is 1. So 1x to the power of n times h to the power of 0. Now, the second term will have the coefficient n. So we'll write plus coefficient n. Now remember that x now will go down 1 power, so n minus 1. H will go up a power, h to the power of 1. And then we're going to have a bunch of terms in here. And we'll write the second last number. Or maybe it's best to start with the very last number. So in the very last number here, we're going to have the coefficient of 1. X will be to the power of 0, and h will have all the powers, so the highest power, n. Now, the second last term will have the coefficient n. So here goes the coefficient n. It's the second last term, which means that x has 1 power, h has 1 power less than in the last term. So, and this will be enough for us to describe the expanded form of x plus h to the power of n. You can imagine that will be an infinite number of terms in here if n approaches infinity. So we'll continue the fraction here. And before we move on to the rest of the expression, we're going to say that the expanded form of x plus h to the power of n is described by this very good-looking expression here. And we'll subtract x to the power of n, this one here. And this will be over h. Now, let's take another look at this expression. We're going to write this in a neater, more simplified form so that we can see things better. And I like to take more steps, so write a little bit more, but make sure that there will be no mistakes in understanding and explaining it. So if we have 1x to the n, h to the 0, this is practically x to the power of n, because h to the 0 is 1, multiplication by 1 won't change anything. The next term will be nx power n minus 1 times h. We'll have a bunch of terms here, and then we'll have nx h to the power of n minus 1. And the very last term will be 1 times x to the power of 0, which is practically equal to 1. So 1 times h to the power of n. So plus h to the power of n. And then, again, this will be the more simplified form of the blue expression. And then we will subtract here x to the power of n. Extend the line. Divide by h. And now let's take another look at this expression. So we are going to look for terms that simplify, and you probably notice how x to the power of n and negative x to the power of n here will simplify to 0. So we'll have to rewrite this limit one more time. We'll say that's the limit as h approaches 0 of nx to the power of n minus 1 times h. And then plus a bunch of terms, and then nx times h to the power of n minus 1 plus h to the power of n over h. Now remember what our goal is. We're trying to simplify h, and we're able to simplify h if and only if every term in the numerator will contain an h to the power of 1, at least an h to the power of 1 as a factor. So I want us to think, if the very first term here has an h, remember that the next term will have an h to the power of 2, the next term h to the power of 3, and the power of h will increase until it hits h to the power of n. So that guarantees that every single term, including the first one that has h to the power of 1, will have h to the power of 1 as a factor. So we'll write the limit as h approaches 0. Long dog fraction one more time. We'll take out h, and then we'll write the rest of the terms in the numerator. So if h is out, then we're left with nx to the power of n minus 1. And then the next term, which we said it will be some term that contains h squared, will still have some h in it. So I will just continue with our ... here, acknowledging and remembering that all these terms that are in here will have an h as a factor. And then we'll continue with this term. So here we have n, we have x, we have h. Now remember that we have taken a power of h to the power of 1, so 1 power of h is out, which will make this h to the power of n minus 2. And then the very last term, from h to the power of n, once h is out, will turn into h to the power of n minus 1. We'll close the brackets, divide by h, and now we can see that we can kick h out of the expression. So time to celebrate. So I'm going to rewrite this one more time, but I think that I need to make this a little bit smaller because we have ran out of room. 1 second. Okay. So here we are. We will rewrite the limit one more time. So we'll do things in proper form here. So we have nx to the power of n minus 1 plus a lot of terms here. They all contain an h as a factor. This must stay inside the brackets to indicate that the entire expression is inside the limit. So now we can make h equals 0 or evaluate this limit. Let's see what we get. Obviously, we no longer have restrictions, so that would make it easy for us to evaluate. So we have nx to the power of n minus 1. This contains no h, so there is no way we can substitute the 0 in here. So that won't change. Now, all the terms that are in between will have an h equals 0 as a factor. Multiplication by 0 will give each term a value of 0. When we substitute h by 0 in this term, then we'll have n times x times 0 to the power of n minus 2. So this term will also turn into 0. H equals 0 means that we have number 0 here to the power of n minus 1, which is also equal to 0. So we're going to say that the rest of the terms in here will be zeros. So therefore, we're going to say that this limit here will simply be n times x to the power of n minus 1. Or in other words, we'll say that f prime of x equals n to the power of x minus times x to the power of n minus 1. So generally speaking, we're going to say that the derivative of x to the power of n equals nx to the power of n minus 1. Or, in Leibniz notation, we'll say d dx of x to the power of n equals n times x to the power of n minus 1.